Today, we're speaking with Hon Weng Chong, who's the CEO of a pretty awesome Australian company called Cortical Labs. I think we actually met at a South by Southwest Sydney
Dinner
event
party.
initially in Melbourne, and then we were on
Yeah.
that panel together in 2023, which was pretty cool. Yeah, I was wondering if you could tell us a little bit about your background and the founding of Cortical Labs.
Yeah. Thanks for having me on the show, Sam. My background actually is in medicine. So studied medicine at the University of Melbourne. Wow, a long time ago now. I graduated in 2012. And I also did a research fellowship at Johns Hopkins, and I was in a clinical elective there. So that's how I have the connections on that side. And then I'm also a self-taught software engineer, which is kind of funny to hear that it's now a profession that's going extinct.
Now that everyone's
We
vibe
all
coding with Claude and, and Codex.
Yeah, with all the AI stuff. I mean, it's kind of funny. I've tried not to use these AI tools because I don't know. I feel like if the brain's like a muscle, if you don't use it, you atrophy kind of thing. And I'm
Yeah.
very worried about cognitive atrophy from not exercising it enough. So occasionally I still go back and do some little coding projects. But yeah, I'm really passionate about technology. I from high school taught myself how to program Mac. And actually, really interestingly, that's how I ended up with a side gig while I was a medical student building mobile apps, because it turned out that the iPhone was just a mini Mac, and I had learned this really weird and obscure language called Objective-C that was actually eventually quite useful. In my final year of medical school, while I was in my clinical elective at Johns Hopkins, I reconnected with a friend of mine who was a developer evangelist at Microsoft and had participated in an event called the Magic Cup, which was really cool. There was a competition run by Microsoft for students to use technology to solve some of the world's toughest problems. And I came up with this idea. Well, actually, he convinced me to do it. I was like, I don't really know about this. Maybe or maybe not. I came back to Australia and I was doing a unit in pediatrics for global health. And it was quite interesting to me to learn that I think it still is the case, but in 2012, the second or third largest killer of children in the developing world was pneumonia. And pneumonia is actually really easily treatable, especially in kids, right? You just determine if they have pneumonia, watch them, and if they deteriorate, give them oxygen and antibiotics. And yeah, I had discovered that it was a problem that was quite common, and misdiagnosis was the number one reason why a lot of people kind of died from that. And so I came up with this idea. What if there was a way for somebody to convert a smartphone into a stethoscope? And so I built a janky little prototype where I ripped out an inline microphone from earpods, took out the electret microphone, shoved it into a stethoscope, connected it up to a phone, and used it like an audio recorder. And it turned out it worked, and it was very good actually. The sound quality was very good, and presented that at the Imagine Cup and actually won the Imagine Cup and got a
Amazing.
$75,000 grant from Microsoft. So yeah, it's interesting as well because part of the conditions of having the grant is you needed to create a company. So I created one, and then I used the money for research. So this was put into research at the Royal Children's Hospital, where we hired a research nurse, and the idea was let's collect a whole bunch of breath sound recordings, and then we can use machine learning or some sort of algorithm to automate diagnosis.
What year was this?
But,
When was this happening? Because this sounds like you're a bit ahead of the curve with a lot of these sort of ML
oh,
approaches to diagnosis.
oh, this was actually in 2013, 2012
Right. Wow.
to 2013. And then 2014, my research nurse told me, hey, do you know, I'm getting a lot of comments from patients because she was going around and recording the lung sounds. She's like, they're asking me, how much does this device cost and where do they buy it? And I was like, but why? It looks like this really janky looking prototype. And she said, well, a lot of patients at the Children's Hospital were actually from the rural and regional areas and had spent a lot of time and money commuting down to Melbourne just for a 30-minute an hour consult. And this is before telemedicine was a thing, right?
Yeah.
And I thought about this, and in 2014, the hype was around internet Internet of Things. So
Yeah.
IoT was the craze.
IoT enabled everything. It,
IoT like toilet bowls,
yeah.
IoT like
IoT in your toaster.
toothbrushes. Exactly. So I was like, why not IoT your medical devices?
Yeah.
And
That's actually more useful, I think, in a
um
lot of the applications I saw at that time.
exactly. So I put my clinical training on hold. Actually, yeah, this was my second year residency. Convinced a mate of mine, well, the American couple as well, who was also a medical student, but decided not to become a doctor and became a management consultant at Bain instead. To put that also on hold, we packed our bags and we went to San Francisco. And we had no idea what we were doing. We had a simple janky prototype, and we just met anyone who gave us introductions. And then along the way, somebody was like, South by Southwest is next week. There's a lot of cool tech stuff. You should go there. So we're like, oh, well, what's there to lose? We still have some money in the bank. Let's go book ourselves a flight. So we decided to fly down to Austin, go to South by Southwest. And it was really cool. And, we met a couple of people. And the best advice I ever got was don't go to any of the day events. All the deals happen at night in the
Yeah.
parties. So we went to the parties and we met one of our early investor friends, a guy by the name of D.A. Wallach, who was like the artist in residence at Spotify. And yeah, a couple of people were like, this is really cool. Here, take some money in an FFF round and see how far you get. So we took that money, went back to Australia, built a better prototype. And then we launched a Kickstarter that caught the attention of the guys at Tencent. And
Right.
they reached out to Andrew, who's my co-founder and CEO at the time, and they said, we like this. We'd like to fund your seed round. And so he was able to actually get us $5 million US, which was quite a lot of money back then, in a seed round to go make these devices. So that's how I got started building hardware and understanding how the supply chains work, sourcing, contract manufacturing, and so on and so forth. Unfortunately, however, this product was a little bit, as you rightly point out, ahead of its time. And we tried to sell it as a B2C play into, Amazon and Best Buy.
Mhm.
And then, we got some sales, but not significant. And then we started to move into the B2B side of things through employee health programs, a little bit more success, but not quite enough to raise another round. And then we decided to put all our eggs in one basket and chase the enterprise deal. And that was actually quite successful. We partnered with a subsidiary from Intel, looking at telemedicine, and secured a deal for 10,000 CL Clinical Lab kit units to the VA. And this was a taste of things to come because this was in 2016 where we had inked the deal. And then in 2017, we were like, hey guys, so we did this deal. Where's the PO? And they said, oh, unfortunately, we cannot issue the PO anymore now because the discretionary expenditure budget has been frozen. And I was like, what do you mean the budget has been frozen? They're like, well, so Trump got elected and he was threatening to rip up Obamacare. But the problem is we don't really know what Trump care looks like. So in an abundance of caution, we've decided to freeze all discretionary expenditures until we get certainty about what's happening. And I was like, okay, cool. He'll hash it out and he'll get a thing out in like 2 to 3 months. No, this went on for 12 months, no, 18 months, as it was going back and forth, the executive branch, the Congress, and back again. And at that point, we're like, oh my God, we're burning runway here, and it's just not tenable. So I exited and closed up that business in 2018. And I think 2017, 2018 was the era of convolutional neural network stuff. It's kind of funny. There are all these thematics, right? And in that time, I wanted to do something in machine learning AI, and I already had the data sets from Clinical Cloud, but you were only as good as the data sets that you had for ConvNets. And it was only a matter of time before big tech would come and eat your lunch because no one had more data than those guys. So I decided to go back into the literature and sort of, read up about which direction I should take. And so I came across a paper written by Dennis Hassabis from DeepMind, and
Yeah,
he
right.
called for machine learning AI people, to return to our roots in neuroscience. And I did exactly that. I went to the University of Melbourne's Neuroscience Department, the Florey Institute, and I said, hey guys, I'm a ex-doctor, washed-up hack founder, entrepreneur who also does machine learning, and I want to know what's exciting in your world, so maybe we can work together. I started to rattle down a whole bunch of things that I was like, yeah, cool, whatever, I'm not interested. And then they said, we have this device called the microelectrode array, where we can grow neurons on this device, and these devices can read the electrical activity of the neurons, the action potentials, and also stimulate them. And I was like, wow, that's really cool. And asked a bit more questions about that. And I said, so when you get these neurons from them, like I said, well, we get a mouse pregnant and then we kill it and take out the brains, shake it in a trypsin bath, causes it to disassociate. And then we take the dissociated neurons and we put them on the chip. And I was like, huh, so had you not done this thing of turning a brain into neurons, then those neurons would have the ability to perform intelligence or exhibit intelligence, right? Like mouse in a cheese maze kind of thing. And at the same time, if intelligence was a form of compute, then therefore these neurons should be able to compute. But why hasn't anyone tried to do this on a chip, right? Because it seems like very logical. So this here, I'm sharing my
Yeah,
screen,
I was going to say
is a
I've seen this up close at your labs in Melbourne, but yeah, maybe give people some idea of exactly what they're looking at here.
yeah, exactly. So this is a microelectrode array, the device that I was talking about. It's not by no means our invention. It's been around for 20 odd years now, but it was primarily used in electrophysiology in research groups looking at ion channel diseases, like, some of it schizophrenic disorders, some motor neuron diseases as well. Also used in cardiac research, anything with electrical field potential. And so these black dots are electrodes. They're about, I think, 50 microns in pitch and diameter. And this is about 200 or 400 microns in pitch. And these are pins, so titanium nitride electrodes, and these are ITO traces. You can think of how they work by having like a sandwich process. So there's glass at the base. We have the electrodes running on top of it, and then we have another piece of glass, but with a masking thing removed, so that the little dots are exposed to the cells, and you insulate the traces from the electrical activity. Um, then on top of this, we have clusters of neurons. So in this one here, you probably have like 50,000 neurons in an agglomeration. I can try and zoom in and show you a bit more what they look like. So it's really dark because there's a lot of them. And because this is light microscopy, if you have a lot of density, light just doesn't go through. And then here, these are the axons that are being spread around. The axons are actually these tiny little lines. These, however, are axonal branches. So neurons like to clump together, and they also like to create like highways of their external connections. So yeah, so you can see this is like suppose several thousand bunches of axons being agglomerated. So yeah, that's essentially a microelectrode array. And yeah, the idea was if this were to be in a brain, it would be able to do intelligence and compute. Who is to say that if it was in this form, it couldn't also do intelligence and compute?
Mm-hmm.
And so that's kind of like the how we end up doing it. And
And this
this
is the product. This is the product that I think I saw up close at the Sydney South by Southwest in 2023 or so. We had the prototypes.
yeah,
This is the CL1 unit, right? It's essentially a human
yep,
neuron run computational platform, wet AI, for lack of a better term.
absolutely. So the CL1 is, let me show you this one. So that was a very early prototype. It was like, hey, look, we kind of know what the shape of it looks like. We kind of know how to put it together. But putting one thing together versus putting like 100 of these things is a different proposition. So what we have here is revision B. As you can tell, it's no longer green. It used to be green, but now it's
Yeah.
just simpler because that way we didn't have to color match and do all sorts of like quality control. But if you ever wonder why everything is white or black, it's
Yeah.
because it's cheaper to manufacture. And so
Doesn't
yeah,
look as
and
cool as green though. I do remember the distinctive sort of green colorway on that first prototype.
it was very cool. And I was thinking, oh, should we keep the green as a legacy thing? But we also went through a bit of a rebrand, and I was like, you know what? Let's just go with black and white. So anyway, this is a CR1, and it's actually, you can think of it as being like a slightly larger shoebox device. So these are 3U rack mountable sleds. 3U meaning that if you put it into a server rack, the height of this is equivalent to 3 shelves of server rack. So this was designed with server racks in mind.
Right. So this
And
thinking about this truly as a plug and play into existing architecture.
exactly, exactly. So we were thinking about maybe it was never really intended for this, but we thought, well, why don't we just build it so that one day we could potentially just rack mount them and just stack them up, right? Because that way we'd be sticking a lot of bench space because bench space is a precious commodity. And in most labs, you have all this like vertical space that never gets used
Yeah,
up.
for sure. Yeah,
Yeah,
vertical agriculture, right? In the Netherlands, one of the
exactly.
biggest food exporters, fresh produce exporters in the world, despite having very little
Yep.
sunlight.
Correct. Yeah. And so we were like, yeah, put them into the server rack. So because that way we can scale it up without taking up bench space. So how it works here is that we have the neurons, they sit in this neural chamber here. which is that same chip with the neurons on it, there are connections here that feed the electrical activity that we pick up from the ADC, the analog digital converters, to a compute unit at the base. So we have a motherboard, we have our processing unit here that's all embedded. There's a 1 terabyte SSD as part of this setup. We have triple diastolic pumps, and we have filtration units here. We have a feeding, we have a waste reservoir, and then we have a gas mixer here.
Mhm. So
And
this is a pretty different design to your average sort of NVIDIA H100 or some other GPU, right? Because you have all these
yeah,
very critical computing components, but you're essentially also trying to keep a bunch of neurons alive in
right.
culture, which is, anyone who's worked in a cell culture lab will tell you is some challenge in itself.
Oh yeah, 100%. And I mean, like everyone's like, "Oh, how do you keep these alive?" And you can actually keep them alive with a lot of work, right? And it's not a trivial matter of taking care of cells because there's all this sterility that you have to deal with and so forth. The question is, how do you deal with the 120 units, which is what we have in our lab in Melbourne? So yeah, this whole perfusion circuit thing was really as a way of enabling us to scale up that biology. And if you scroll to the back here, you end up with some very interesting stuff. This is the I/O panel. So you have your typical Ethernet, USB-A, and USB-C, but these 3 plugs here are actually for gas. So the inlets are air,
Definitely not standard in
CO2,
a
and nitrogen.
GPU.
Not standard as the GPU, right? So air, nitrogen, and CO2. And we have this, we call this the FARC valve. It's actually a outlet valve, just in
Right,
case we have buildup of pressure inside, it can come out.
right.
And yeah, so this is the CL1 device.
Do you
So
need any kind of special, as just thought of it then, any kind of special containment for the outlet gas, given that it's sort of biological in origin, or you have it filtered and it's fine?
no, yeah, we actually don't even have it filtered. We just like
All
let it
right,
come out because
right.
because it's just gas. So it's lab grade like CO2, filtered room air, and what's the other one? Oh yeah, just nitrogen, right? So we use nitrogen to drop the oxygen concentrations down to more physiological, like 5% levels. Having said that, we've kind of been lazy and not been bothered to hook up the nitrogen for a while now, and we haven't really needed to do too much of it because we haven't done too much long-term experimentation. So whatever oxidative stress the neurons get, it's only for a month, so we don't really bother too much.
Right,
But there is that ability to actually drop the oxygen concentrations down to about 5%, which is more physiologically relevant.
right.
But I'm going to show this here as well. So when I talk about rack mountable sleds, this is what I actually mean. They are in server rack cabinets, and each one of these will contain about 200,000 neurons. And in one rack, you can fit 20 units. Actually, you probably could fit 30, but it's a bit too much of a tight squeeze, so we spaced them out a little bit. And these are 45 U's, so 45 shelves server cabinets. So yeah, that's the CL1, and now we have the ability to manufacture these, and we have several universities and labs already using them. So they are in the wild now. So Dartmouth has one, UC is getting it two, Melbourne
Cool.
Uni are getting three. Actually, the Melbourne Uni is getting one, Monash is getting two. National University of Singapore ordered a rack, so they're getting 20 of these. Yeah, and so that's really exciting stuff for us.
So there's a lot's happened since I last saw you, clearly, and I've been tracking it online. And we'll get to some of the sort of recent PR that I've seen shortly. But what's the energy requirements on one of these units versus a traditional kind of all silicon processing unit?
Let's say the only energy we really use is for running the compute unit. And so the compute unit uses about 25, well, the entire unit uses about 25 watts, but it's actually a mobile chip with an FPGA component part of it. So one CL1 will consume about 25 watts of energy. The actual neurons computing it will probably only use 10 to the -4, -5 watts of energy. And this is assuming complete combustion of the glucose, right, in the cell culture
Yeah.
media. And so yeah, it's very low energy requiring, and also it generates almost no heat.
Yeah,
So this
exactly.
is running in a lab in the standard like lab environment, standard lab HVAC, no crazy cooling required.
And qualitatively, what are some differences between a traditional the GPU setup and the sorts of computation you can do with these units?
Yeah, so I think if I go back to why this approach is, let me show you. If you think about like computers, right, there are some very strong things that they do, like perfect memory preservation and retrieval. fast, deterministic compute, right? These are all things that we find useful, but we're entering this age of intelligence. And intelligence deals with very noisy environments, noisy signals, and actually being perfect and completely deterministic is actually a detriment to autonomous systems. So autonomous systems need to have that flexibility of fluid intelligence, online learning, world models, abstract reasoning, and so forth. And I think, what we're looking at, and I think that the guys in the BCI space are also doing, is how do you bring the best of both worlds, right? How do you take a very fast deterministic computer, put it in your head? So if you are thinking about, I don't know, let's say you're a footballer, right? And you need to kick a ball through the goals or whatever. And there's a win thing. If you could compute all of that perfectly as a trajectory, and as the gameplay is happening, you can respond very quickly, you'd be like a superstar player, right? So I think this is an example of how you could meld the two together to get something that's greater than the sum of its parts.
Hmm.
And to answer your question, these things are not good at hashing Bitcoin. These things are not
Yeah.
good at large language models, which are essentially just very large information data repositories and retrieval and synthesis. What they will be very good at are things like robotics, embodied intelligence, physical AI, real-time systems, where there was no body of corpus to learn from data. There was not enough time to train on and pre-train on. And you
Right.
have to make these very fast decision-making processes. And so time is actually the most important factor of why these things are actually useful. You're probably wondering, like, how do we actually get these things to train and learn?
Hmm.
And there are many different ways of doing it and different theories, but here's one that I quite particularly like. So this came from our research paper
Yeah.
in 2022 for the Pong thing.
Yeah, I remember
And
reading about this, and there's an interesting sort of parallel here with Demis Hassabis and DeepMind because they were
yeah,
teaching these sort of reinforcement learning agents to play early Atari 2600 games. I thought this was kind of a nice parallel that you're also using this as an interesting sort of training platform.
yeah, absolutely, right. I mean, again, so this is something these things are very good at, which is control systems. They're good at controlling that paddle in real time and responding to signals. And the way we actually do this is the Pong world is happening in a computer program. We're taking information of where the position of the ball is to the paddle in the X and Y axis and feeding it in as a mixture of place and rate coding on the sensory region. And then we give it a short period of time and we sample the outputs of these neurons. We take the outputs and we feed it back into the computer program. And you do this loop over and over again. So this is an effect creating like a pseudo matrix environment where the neurons are receiving information from a computer program and they're responding to that. And that's the only input output they're getting in terms of an information system. And that's not enough. It turns out you also do need to reinforce the
I,
behavior.
I was
And
about to say, how are you rewarding correct behavior here? Because this was an interesting self-amplification in the early deep Q network kind of approach. How do you
yes,
provide sort of reward and reinforcement here?
so this is based on the free energy principle, which is theory or framework developed by Carl Friston at UCL, which posits that biological systems, brains, neurons, and supposed to be scale-free Bayesian generative machines. And what it actually means is that internally, you and I, we have a belief of what the world is, a prior distribution of our beliefs of what the world is. The real world has its own distribution, its own sets of like rules and so forth. So, for instance, gravity is a distribution because everything is on the ground as opposed to being floating in three-dimensional space. And it's part, I guess, of an evolution to get very good at refining our internal models such that they actually make extremely good predictions of what the external world is. Because if you think about if you can better predict the external world, you have better survivability. If you're prey, you can run away quicker because you know the wolf is coming. If you're a predator, you can hunt better because you can predict which way, or you can predict this something in the grass is probably like a rabbit that you can just go munch on. And so biological systems have evolved to actually get very good at predicting the external environment. And we exploit this property by feeding in predictable signals to reduce the overall information entropy and thereby bringing the two distributions closer together and pushing them apart with unpredictable information. And it turns out this kind of works as a theory. But I think there's also a very simple explanation too, which is that if hairpin plasticity is a thing, and I haven't done the numbers, we haven't really done it, it's kind of intuitive. If hairpin plasticity is a thing, and for hairpin plasticity to be happening, you need to have coincidental signals, then you have a high probability of coincidental signals when your signals are predictable to begin with, right? As opposed to random chance, random noise signals. So if you're going down the hairpin plasticity route, having predictable information signals is going to reinforce the behavior just by having the synaptic coincidental firings.
Very cool.
Yeah.
And so you've used Pong sort of to illustrate this principle, right? I remember seeing the paper when it came out. What I wasn't aware of until recently is that you're now offering sort of other users access to this platform to do their
Yep.
own sort of development work, right? I think I
Yep.
saw an interesting publication recently because, we have to take any bit of available computation in the world and any consumer hardware and force it to play Doom. I saw that someone has actually attempted to use this system to run
Yep.
Doom, right? Which is really a sort of more advanced version of Pong in a lot of ways.
100%. And it's very fulfilling for me to see this, right? Because for the longest time, we will always want to do exactly that, which is build a machine and get Doom running on it. Um, and the problem is we've been so busy for the last 3.5 years building the thing, building the APIs and SDK that we never really got a chance to do that, right? And so we ran a hackathon at Stanford, a remote hackathon, where we gave students our API and SDK and several hours of neuron application time to test their code on. And one student, Sean, was able to take our API and SDK and a little bit of help later on from us, make a Doom agent learn how to play. So this is a screen recording of the system getting primed and being connected. And what he did was quite interesting. He built a tandem RL system. So there was a reinforcement learning agent running in the same time as the game was happening, refining every episodes to improve the performance. And so that Doom agent is being controlled by the neurons. And it actually performs, and we were like shocked when we saw this. We're like, is this real? We were like, did you run the ablations? And he said, yeah. So we looked at the numbers on the ablation and we're like, wow, okay. So if you remove the neurons, it falls back to baseline. And baseline is it
Right.
gets shot pretty quickly and it just randomly does stuff with no intention.
So what we're looking at here is sort of 200,000 or so, or sets of 200,000 or so disembodied neurons sitting on a server rack somewhere,
Yep.
learning how to play Doom by reinforcement.
Absolutely. I know we live in wacky times, right?
I think I
Actually,
think
I'm gonna.
Gibson is probably very impressed by all of this. I haven't seen him writing about it recently, but I'm sure he's tracking all of it very closely.
Oh yeah, for sure. Oh, but actually, here you want to see this? So this is Sean who came to visit our lab, and he very proudly posted his set of neurons on Twitter. That's his machine that he used to train the system on.
I'm sure he was extremely proud to be able to visit it and check it out up close. It's pretty neat. Let's take a look at this interface then.
Yep. All right. So this is a interface into a remote CL1 machine. So when you get a CL1, you get the operating system and the software as part of the system. And this is your dashboard. So you get to see the vitals, the pump speeds, system version, uptime, storage, and so forth. And then you get this view here of a topological layout of the electrodes on the chip, and we flash the spikes every time it's being detected by spike detectors. And at the same time, we also have the intensity, so how frequently we're detecting the spikes. This is a raster plot, so you can imagine if we were to take the electrodes and roll them out in a line, this is what you would get. And this gives us a really good way of viewing the spike correlation in terms of a time domain and time series. So that is kind of cool, but then we also get an actual spiking view here. So what's really cool about all of this interface is that it's all being built using our internal API and SDK. Hence the reason why we never had time to actually make Doom to work, because we were working on all of this tooling stuff. So we can see this view. We can also provide a stimulus. So if I were to click here, I've now delivered a stim into the network, and I can do another one here. Let's say, then you get changes to the network behavior depending on the pattern of stimulus. So you see how that one kind of got quieter after I gave a stim. We can also see there's a 3D view. So if I wanted to go in, I can zoom in this way and I can move around to explore, what the spikes look like. But we also have a spike view. So this is the actual waveforms that are being detected and we're visualizing it and drawing it in real time. The way you do this is you install applications. So we have a couple of them installed, like Pong and so forth. And for instance, a game with associated assigned lectures B, Y, C, Y, Pong, and we give you summary statistics. You can view the output and you can download the actual recording. So this is what, 11 gigabytes of data from a gameplay session. And we have these applications that we pre-install, but you can bundle them up and share it with your colleagues or with other people, and just throwing it into this install new application zip package. We'll unpack it all and install it for you to run the applications. But the way you actually develop it is Jupyter Notebooks. Yeah.
Yeah, I love Jupyter Notebooks.
Exactly. So like, let's say I want to see real-time visualization. This gives you some sample code into how to do it. So yeah, this is how you would program the system in Jupyter Notebooks, and then API and SDK. It's coming soon. We haven't rolled out a new version yet, but there'll be a one-click export button that will allow you to actually package up all your Jupyter code into Python with whatever associated data is required, bundle it together, and then install it into another machine so you can share them around. And yeah, so recording, we can see a whole bunch of recordings here, the documentation, user manual is built into the system here. So yeah.
Amazing. Yeah, I'm super excited to see what people start doing with this. That's awesome. Awesome. I can think of a lot of things where, this compromise between pure silicon computing and this more brain-like computing could actually be super useful. What are some of the sort of future applications that you could envision down the road?
Yeah, so I think is knowing the true strengths and properties of the system is going to guide its applications. Where would these be useful for? So anything that has a real-time setting where there's a dynamically changing environment, this would be good for it. So the simplest example, like Doom is one thing. The neurons are controlling the Doom guy. But who's to say neurons couldn't actually just control NPCs in a game world, right? And you end up with much richer, more immersive game environments, right? So the gaming sector is probably one that we'll probably work with because A, it's kind of fun, and B, it's a great place to test new technologies because the worst thing that happens is, oh, well, the game sucked or the game crashed and no one gets hurt.
Yeah.
Putting them into robots, on the other hand,
Sure.
you break your robot, or even worse, your robot breaks a human. That's a lot more riskier. So I think, games is one, robotics, physical AI, embodied systems is going to be another one. And then, there are a whole bunch of other things that have tight constraints, right? So for instance, cybersecurity in network security intrusions, not like looking through code and trying to find exploits, which is what Claude Mythos is doing. But let's say it's a closed source thing. You can't see what the code is, but you now have a network intrusion. You got to figure out what's going on. Is a hacker destroying my network and so forth? And AI systems just don't do very well at that because there is no data to pre-train on. That's why they're called zero-day exploits. The other one that's pretty useful for is potentially trading, right? It's a dynamically changing environment.
Right. Yeah.
And you can't pre-train the rules and, there's no precedence for some events. How do you respond to them? And perhaps maybe this might be an application. Not that I condone losing your savings by getting these things to trade, but who knows? Maybe it might actually be quite good on your behalf.
Whose neurons are being used in these systems is a good point, actually, because I mean, theoretically, subject to the right approach to ethics, you could use your own neurons, right, from stem cells or something else.
And that I have done.
You have?
So yeah, so some of the neurons, actually a lot of the cloud neurons are actually my neurons because
Right.
I feel like I'm the only one, or only the founders really can understand and can consent to something like this.
Right.
And I think informed consent is really important at this stage. Because, for instance, what if
Did
somebody
a Human Research Ethics Committee in Australia have to sign off on this?
Yeah, they did.
Right.
Yeah.
Seen one like that quite before.
Well, I mean, it was for research and it still is for research. It's just now that it's used for research, it is still governed by what we can and can't do. It's just now more accessible to people to do experimental work. And we're not doing anything too drastic to the cells. But I think more and more important is the commercial question of if somebody were to build $1 trillion business, like let's say an OpenAI came out from our system and somebody donated the cells to make that happen. do they have a right to a percentage of that trillion-dollar business because it was built off their genome, right?
Yeah, yeah. Get some pretty interesting bioethics quandaries here for sure.
Yeah, right. So this is the whole Henrietta Lacks situation. So, the most important thing is informed consent. So I feel like this is my company, so whatever.
Sure,
It
sure.
works out, it works out.
Sure. Yeah. I mean, if you're building the product, literally, I think you're in a position to give the most informed consent probably of anyone who's seen the technology. That makes sense.
Absolutely. And I also like to joke that this is literally my blood, sweat, and tears now.
That's awesome. That's so cool. Well, I'm
Yep.
excited to catch up in person next time I'm in Melbourne for sure.
Oh yeah, for sure.
Yeah, thanks so much for jumping on, reaching
No
out.
worries. No worries. Thanks, Sam.